Good evening, everyone, and welcome to the Daresbury Laboratory Talking Science programme. It's lovely to have you join us this evening. This is the first talk of 2022. I have no idea where the time has gone since we had our last talk in December, but it's lovely that you can join us tonight. So for those who don't know me, my name is Wendy, and I work in the Public Engagement team at Daresbury Laboratory. And we work for the Science and Technology Facilities Council, or STFC. So who is STFC? Well, we're one of Europe's largest research organisations. We enable the UK's natural sciences, together with the computing and engineering communities, to carry out their world-leading research. And we do this by working with universities, national laboratories, regional campuses, and scientific facilities right across the UK and abroad. We study a whole range of science, from the smallest particles that we know of, right through to the objects in outer space and the mysteries of our universe. So for those who don't know, we have a number of sites around the UK, and it's quite a privilege that we do have this spread of different labs in different parts of the country. So starting down at the bottom, we've got the Rutherford Appleton Laboratory in Oxfordshire. It's our largest site and covers research in particle physics, scientific computing, laser development, and space science. That's where tonight's speaker is actually based. At the bottom, we've got Chilbolton Observatory in Hampshire, which is much smaller, carries out research in atmospheric science, radio communications and astronomy. Polaris House in Swindon is the STFC headquarters. Daresbury Laboratory in Cheshire in the northwest, who is hosting tonight's talk, is internationally recognised for its work in nuclear physics, high performance computing and accelerator science and technology. One of our prettiest sites is based in Edinburgh, of course it would be, and is a UK Centre of Excellence for ground and space-based astronomy. And finally, we have an amazing site near Whitby on the northeast coast, 1.1 kilometres underground at the bottom of a working potash mine, studying science in a really unique environment. So as you can see, we're well represented across the UK in a diversity of fields that underpin the UK's contribution to science. And we do love to talk about science, so public engagement is really, really important to us. So I'm going to introduce tonight's speaker now. We have Dr. Chris Pearson. Chris has a PhD in galaxy evolution and cosmology. He has worked on cosmological galaxy surveys at infrared wavelengths for both ground-based telescopes and spaceborne missions. He has worked for 7 years in Japan, amazing, on the Akari Space Telescope before moving to the UK to Vowel Space. He has worked on the Spire instrument for the Herschel Space Observatory, where he led the team that produced all the nice maps from Spire. He now works on the Ariel mission, searching for exoplanets, so cool, and the Square Kilometre Array Radio Telescope, which is the largest scientific facility ever to be built. Believe me, it's worth reading up about the Square Kilometre Array because it is literally mind-blowing. So as you can see, Chris has a wealth of experience and we're really delighted to have him talk for us this evening. So Chris, it's over to you.
Okay, thanks. So should be able to see my screen now?
Yes, thank you.
Great. So thanks for inviting me here. My name's Chris Pearson. I work at Vowel Space, Rutherford Appleton Laboratory, and I'm a cosmologist by trade. But today I'm going to talk to you about the life of an atom, or what we could think of it as the journey of an atom from its birth to where we are today. So, quite topical. On the background on my front slide, I've got one of these beautiful astronomical pictures. This is the Vowel Nebula. It's the aftermath of an exploding star. It's about 8,000, happened about 8,000 years ago. So this is like the smoking gun. The entire nebula is about 100 light years across, which is about 6 full moons on the night sky. And these sorts of places in the universe are rich in elements. We see hydrogen, we see helium, carbon, nitrogen, oxygen, and these form the basis of basically what I'm going to talk about today. So I can start off with a somewhat profound statement, first of all, here, where we are all made of stardust. And I'm sure a lot of you have seen this phrase before. It was made popular in the 1970s by Carl Sagan in one of his books. And you know, the basics of it is that the rocks we stand on, the iron in our blood, the calcium in our teeth, the carbon in our genes, and the gold in our jewelry, they were all produced billions of years ago in the interiors of stars. So indeed, you know, we are very much made of stardust. And this has been, you know, jumped on by commercial interest. We're all made of stardust bumper stickers. You can get cushions. You can get vinyl stickers, you can even get t-shirts with it on. Indeed, we are all made of stardust. But what are we really made of? Okay, specifically, we're made of rather, not so romantically, 65% oxygen, 18% carbon, 10% hydrogen, and 3% nitrogen. So this is the makeup of the human body. There's also a host of other elements that make up our bodies, so calcium, phosphorus, potassium, sulfur, all the way down. We've even got a little bit of gold in our body as well. It's about 0.02 milligrams, which I checked today, today's gold prices, that would be less than a penny if you could extract all the gold from your body. So I wouldn't try too hard with doing that. The average human body contains something like 7 octillion atoms of various kinds. So octillion is 10 followed by 27 zeros. And inside our body, we've got about 60 or so chemical elements, different types of atoms. So it's worth talking about, you know, when I say atoms, what do I mean? Atoms are the stuff we're made of. The simplest atom is hydrogen. So up in the top left, there's a little diagram of the hydrogen atom, and it's like a little mini solar system. At the middle, we've got the red ball is a proton. It's got a positive charge, and around the proton, there's orbits and electron, the little blue circle with a negative charge. And as we move up through the elements, they get more and more complex. So we move to helium. So He is the chemical symbol for helium. Helium's got 2 positive protons in the middle. They're the red dots. It's also got 2 neutrons. They're 0 charge. So 4 particles make up the nucleus of a helium atom. So these elements have got numbers. The red numbers here are the number of protons. So we've got 1 for hydrogen, 2 for helium, 8 for oxygen. And the top numbers are the number of protons plus the number of neutrons. So you've got 1 for hydrogen, because there's only 1 proton. You've got 1, 2, 3, 4 for helium, 16 red and yellow dots for the oxygen atom. Then we get more and more complex, where we get the nucleus looking a bit like a corn on the cob there for gold, with 79 protons and 118 neutrons, making a total weight, as we call it, of 197. However, most of the space in atoms is empty. We've got the nucleus tucked together right at the center. The actual atom's about 100,000 times bigger than the actual nucleus itself. Most of it, an atom, is empty space. If you think of an atom as Wembley Stadium, then probably the nucleus would be like a football on the center spot. So, and the rest of the space would be little ball bearing size electrons whizzing around the atom. Okay, so I've introduced 4 elements here. A lot of you probably know there's a whole host of elements. When we were at school, or some of you are at school, you've got the periodic table. Every chemist's dream and every school child's nightmare, perhaps. So this is the periodic table of elements. It contains every single thing that was ever made in the universe. So you've got the number of protons from 1, 2, 3, 4, 5, 6, 7, 8, all the way down to 118, right? There are no numbers missing on this table, right? It's not always true. When the table was first conceived, it's a guy called Mendeleev first created the table in 1869. There were holes in it because some elements hadn't been discovered. But those holes were used to predict the properties of the corresponding elements that were later discovered. And in fact, some of these elements, for example, you've got number 43, if I can find it, there's 43 there. Technetium, it wasn't discovered until the 1920s because there was no stable version of it. Anything above 93, anything above Neptunian here is artificially created by humans, doesn't exist naturally in nature. But where do all the elements come from? So to answer this question, first of all, we have to go back to the beginning of time. We have to go back to the Big Bang at the beginning of the universe, 13.7 billion years ago. So the Big Bang was the creation of space. It was the creation of time. Nothing else has been created since the Big Bang. Nothing existed before the Big Bang. So all the things you see around you, the stars, the planet, the life around you, it's all been built from the Big Bang. Okay, but what was around at the Big Bang? Obviously, we didn't have every single element on the periodic table. Things were simpler back then. And in fact, at the Big Bang, the universe was a soup of neutrons and protons and electrons. And these are all whizzing around. The temperature's really, really high. Sometimes a neutron and a proton get together, they hit each other, and they stick together. And they stick together to form what we call hydrogen 2, because there's a proton and a neutron, so two things in the middle and one proton. This is often referred to as deuterium. So they stick together to form deuterium, and then two deuterium atoms can come together, they can meet, and they hit each other, and they can form a helium-3 atom. So again, two protons, so it must be helium, one neutron, so helium-3, and one neutron gets ejected. And then this helium-3 atom can again meet up with another deuterium and form helium-4, which is the common helium that we see on the periodic table. So in this way, the elements are slowly being built up in the Big Bang. In fact, almost all the hydrogen nuclei are protons that emerged from the Big Bang. The hydrogen in our bodies, some of it is going to come from the Big Bang indeed. So why can't we build up the whole universe like this? Why can't we build up the whole periodic table? The reason is it's tough to make elements. It's a real race to build the elements, because after about the first 3 minutes after the Big Bang, the universe cools down and the reactions stop. It's simply not enough energy to make the heavier elements. It's not helped by this little ladder here where we go from hydrogen, we go up to 2, 3, 4, and there's a gap between 4 and 6 between helium and lithium. It's difficult to make an element by jumping over that gap. It's possible, some little bits of lithium are made. Then there's another gap between lithium and beryllium. You have to jump that gap here. Problem is, beryllium is unstable and decays back down to helium or lighter elements again. So we can form in the Big Bang 3 things, mostly hydrogen. It's about 75% hydrogen, about 25% helium, and a tiny bit of lithium in the Big Bang. So if we were in a chemistry class back at the dawn of creation, chemistry would be pretty simple, because this would be our periodic table. This is our periodic table after Big Bang, 3 elements. Wouldn't GCSE chemistry be simple if it was only like that? Unfortunately, there's lots of unticked boxes to fill up, which we're going to do. But this is where we were after the Big Bang, and indeed probably, for about 300, 400,000 years after Big Bang, where we have a picture of the baby universe. So this is a picture of the universe as it was about 380,000 years after the universe was created in the Big Bang. The universe is cooled enough now, so you're seeing hot spots and cool spots in the red and blue, and the hydrogen and helium can start to clump together to form some kind of structure. So what's going to be the galaxies and the stars that we see in the future. So astronomers can run simulations like this, and we can see one here where we see a nice uniform universe slowly clump together, and we form these filaments, these long filaments, and these little nexuses as well that we're going to fly through now. These little nexuses are going to end up being the big clusters of galaxies, or the giant galaxies that we see today. So we're just going to zoom in on what will become one of these giant clusters of galaxies. So we've moved from the Big Bang to forming the first galaxies, something like about 300 million years after the Big Bang. Astronomers call this the cosmic dawn, where the first stars and galaxies were formed. So what is a galaxy? A galaxy is basically a city of stars. This image here is a picture of M31, the big Andromeda galaxy. It's the nearest galaxy to us in the sky. It's also the only thing outside our own galaxy that you can see with the naked eye. It's about 2.5 million light years away, which means even traveling at the speed of light, it would take you 2.5 million years to get there. So we're not going to go there anytime soon. We don't live in this one. We live in the Milky Way. We think the Milky Way looks very much like Andromeda. We think we're kind of twins in the universe. So we can't step outside our own galaxy to see a picture like this. What we can do, if we go somewhere dark we can look up at the night sky and we can see this thick band of stars moving across the night sky here. Again, you have to go somewhere where there's not much light to see this. I was lucky enough once to be in the desert in Egypt, and that's the best view I've had of the Milky Way, because clearly there were no lights in the desert. So that middle bit, that band of stars, is looking through the disk outwards, and all the other dots of light in the picture are also stars, but spread out around a sphere around the Milky Way. So our own galaxy is the Milky Way. Every single dot is a star on this. So stars are the basic building blocks of galaxies, and there's about at least 100 billion stars in our own Milky Way. Here we have a really good example of a little star cluster. This is the Pleiades, also known as the Seven Sisters. The Pleiades in Greek mythology were the seven daughters of the Titan god Atlas. It's about 450 light years away in the constellation of Taurus. In Japanese, we call this constellation Subaru, and of course it was taken on board by the car company. There's the Subaru car company, and you see the emblem for the Subaru car company is the Seven Sisters. It's actually six sisters there, because we can only actually see six of them with the naked eye, because two of them are so close together. So Subaru in Japanese, it was formed by a merger of Fuji Heavy Industries and 5 other companies, hence the 6 stars, with the big star being Fuji Heavy Industries. Just a little aside for car enthusiasts there. But we're doing astronomy. So here's the stars. Our closest star is the sun. This is our own star. Stars are giant balls of hydrogen and helium gas, and the sun is one of 100 billion stars in the Milky Way. The sun's about 300,000 times heavier than the Earth, and you could fit about 100 Earths, about 109 Earths across the diameter of the sun. The sun is truly immense. Even at 93 million miles away, 150 million kilometers away, when the sun comes out, immediately you feel warm. Yeah, it's a powerful star. It's about 73% hydrogen, 25% helium. At the surface, temperature is about 6,000 degrees Celsius. That's hot enough to melt any element. Think the tungsten element has the highest melting point of like 3,400 Celsius. Nowhere near the temperature of the surface of the sun. But inside the sun, if we open the sun up, we see the surface around the convection zone, we see a radiative zone, but in the middle is the core. Now, the core is the nuclear factory in the sun. The core is where all the power is being generated, the energy that makes the sun shine. Without the core, the sun would just be dim. We wouldn't see anything. It wouldn't be shining at all. It's about 1/5 to 1/4 the size of the whole sun itself, and in the core it's something like 15 million degrees Celsius. 15 million degrees Celsius. So incredibly hot enough to make nuclear reactions take place. So there's 2 different types of nuclear reactions, and this is going to be important when we talk about the elements. There's nuclear fission, where we take a big nucleus, big atom, and we split that atom up into parts. Here we have an example of nuclear fission of uranium breaking into barium and krypton atoms. Nuclear fission was first used in the atomic bombs on Hiroshima and Nagasaki, but these days it's used in much more controlled circumstances in power stations. It's how nuclear power stations get their energy. What we'd like to do, though, is nuclear fusion. Nuclear fusion is not splitting atoms apart, it's pushing atoms together. So in this case, we've got a couple of hydrogen atoms that we push together to make a helium atom. And when that helium atom is produced, the energy of pushing those atoms together is given off as fusion energy. So the fusion energy is actually much more efficient than the fission. It's about 4 times more efficient. And one day we hope to have fusion powered nuclear reactors. There's a lot of places in the UK. There's places like Culham in the UK and ITAR in Europe that are actually seriously trying to make fusion work. But fusion is how stars get their energy, and our sun is no exception to that. So this is our sun. If we could open up the core, what we see is basically the sun is a big nuclear power station. And we start off with 4 hydrogen atoms, 4 red dots here, and we go through a various set of different types of reactions down to helium-3, a couple of helium-3 atoms get together, they stick together and give off energy infusion, and eventually we end up with this helium-4 atom in the center of our sun. So the sun shines because it converts 4 hydrogen atoms into 1 helium atom. This is called the proton-proton cycle. And the sun's converting about 600 million tons of hydrogen into helium every second. So it's a very efficient power station, the sun, which makes the sun shine. But the sun, like anything, it has a lifetime. It was born something like 4.5 billion years in the past. It's about halfway through its life now. So here we've got the life cycle of the sun. We sit where this blue arrow is here after about 4.5 billion years. But we can look at, on the bottom here, this shows the fraction of hydrogen to helium in the sun. When the sun was born, almost all of it was hydrogen and helium, well mixed as well. So there's no difference between the core and the outer atmosphere of the sun. Now, after about 5 billion years or so, the sun has converted about half the hydrogen in its core into helium. That's about halfway through its life. As the sun gets older, it converts more hydrogen into helium, and the core fills up with helium. And the sun shines brighter and brighter. In fact, the sun's about 30% brighter now compared to about when the Earth was formed, and it will become about 1% brighter every 100 million years or so from now. After about 10 billion years, the sun's reached the end of its life. It's used up all its hydrogen in the core. There's no more hydrogen left to burn. All the core's helium. There's no more fuel. And gravity takes over and starts to make the sun contract, and the atmosphere. So the middle of the sun contracts and the outer parts of the atmosphere start to fall away. And this is the death of our sun. Don't worry, it's not going to happen tomorrow. You've still got that 5 billion years before this happens. When the sun dies, it doesn't go out with a big bang. It goes out with a bit of a whimper, I'm afraid. As a sun-type star dies, it becomes what we call a red giant. It expands to many, many times its own size. When our sun becomes a red giant, I'm afraid it's going to eat up Mercury. It's going to eat up Venus. It's probably going to burn up the Earth to a cinder as well. But again, don't worry, 5 billion years. Don't have to worry about that like next week, next month. We have time. It's okay. So red giants, things start to move fast. Red giants only last for about 100 million years. The core of red giant gets so hot that it can take helium atoms in the core and throw those together, get 3 helium atoms, throw them together and create carbon. And this is called a helium flash, or we call it the triple alpha process as well. Basically, we're moving away from hydrogen. We're taking 1 helium atom, 2 helium atoms, making a beryllium atom, and before that beryllium atom can disappear, we whack it again with another helium and produce carbon. So our sun can produce carbon in the later stages of its life. And in fact, there's other ways we can actually make other elements as well. We start with carbon, we can move around this circle to make nitrogen, to make oxygen as well. So we call this the CNO cycle, carbon, nitrogen, oxygen cycle. So in this way, our stars like our sun can also make heavier elements like carbon, nitrogen, and oxygen. When the sun dies, as I said, it goes out in a whimper. It makes these beautiful planetary nebulae. It throws off its outer atmosphere and makes these beautiful astronomical images. This is the Ring Nebula, about 2,000 light years away from Earth in the constellation of Lyra. This is a Hubble Space Telescope image. And the blue on this, the blue gas is the helium. The green is the ionized oxygen. And the red, I believe, is nitrogen. This is all elements that have been thrown off from the sun-like star when it's ended its life out into space. Left at the middle is a really, really hot cinder, the aftermath of what our sun will become. It's a white dwarf star, absolutely tiny in size, but a big, nice, beautiful end to the sun's life. So where are we? We've now managed to we've come about 13 billion years, and we've managed to add like 3 more to the table. I've also added 2 in pink, boron and beryllium, not made in stars with a big bang. They're made kind of like rather boringly by cosmic rays. So we won't talk about those today, but we'll talk about carbon, nitrogen, and oxygen. So these are made in stars like our sun. But clearly, if we want to make more elements on the periodic table, we're going to need a bigger star. Okay, so high mass stars, bigger than about 3 times the size of our sun, can start to burn heavier elements. So here's like this is called the Hurstbound-Russell diagram. It's kind of like a personality diagram for stars. So we've got our sun down here. This is temperature on the bottom. So our sun, it's reasonably hot temperature, 6,000 degrees at its surface. But bigger stars become brighter and they become hotter. So we've got the sun here, it's a yellow star. We've got Sirius, the dog star, is a white star. Then we start moving up to bigger and bigger stars. We've got Eta Aurigae here. It's 243 light years away. 5.5 times the mass of the sun, 900 times as bright. And then we've got big blue supergiants. This one, for example, this could be Alnilam, which is the one of the stars in Orion. It's the 4th brightest star in Orion. And together with 2 other stars, Mintaka and Alniak, it makes up Orion's belt. So you can see this star in the night sky. This star here is 500,000 times brighter than our sun, and it's about 40 times as massive. And these big giants are going to be the nuclear factories that we can use to build the heavier elements on the periodic table. So again, we're starting to build more elements now. We're starting to move up now from carbon, nitrogen, oxygen. These big stars can create fluorine, neon, magnesium, silicon, sulfur. We're going to go all the way up to iron. But this picture here shows the abundance of the elements. So how many elements there are compared to other elements. It's what we call a log plot. So it's not 1, 2, 3, 4, 5, 6 up to 12. Every time we move up 1, it's like times in by 10. Okay, so if I go from 11 to 12, that means there's more than 10 times more hydrogen than helium. Yeah, okay, or close enough, right? If we look at oxygen and nitrogen, there's about 10 times more oxygen than there is nitrogen. So even though it's 1 on the table here, it's a jump of 10, a factor of 10. So oxygen is the most abundant element in the universe after hydrogen and helium. You also notice there's carbon and nitrogen, oxygen are like the top 3 after hydrogen and helium. And it's no coincidence that our bodies are made up of carbon, oxygen, and nitrogen, because they're the most common elements in the universe. So it stands to reason that most of our bodies will be made up from the common elements as well. What we also notice is this zigzag line up and down here. So it looks like some elements are more common than others. In fact, the elements at the top of the zigzag are about 10 times more common than the odd numbered ones. So let's just put those lines down there so we can see them. So we go up, down, up, down, up, down, up, down, up, down, up, down. So why is this? And in fact, if I put the atomic weights on them here, we can see actually, atomic numbers, sorry, we can see that they're all even numbers. So why are the even numbered elements more common than the odd numbered elements? And this has got to do with how the elements are built up inside stars. So again, if we're making oxygen, so the O, we can make oxygen by colliding a helium atom with a carbon atom, and that will make oxygen. If we want to take oxygen and make neon, we collide a helium atom with an oxygen atom to make neon, and 2 carbons to come together to make magnesium, and then we get 2 oxygens to get here to make silicon plus an extra helium. So what we're seeing here is the building blocks of carbon and oxygen are helium atoms, so sets of 4 or even numbers. So we can take this to even heavier elements here, and we can see again silicon to sulfur, add a helium, sulfur to argon, add a helium here, argon to calcium, add a helium, and so on and so on and so on. So we're finding that helium is kind of like the basic building block of nuclear reactions inside stars, and we go all the way up to iron at 26. Okay, and then things stop at iron. Okay, so we'll come to that in a minute, but we've managed now to fill up our periodic table with our big stars, and it's starting to look a little bit more, you know, challenging from a chemistry class point of view now. We've got all the red elements that have been added due to their creation in big stars, but still we're missing a whole chunk of that periodic table. So, you know, where does this come from? You know, it comes from bigger stars, I guess, right? So stars can fall into two categories, right? Big ones and small ones here. Small ones, like our sun. We've spoken about how the sun lives its life. It lives for about 10 billion years. It becomes a red giant at the end of its lifetime. And then it throws off its atmosphere, becomes one of these beautiful planetary nebula, and ends up as this white dwarf, like the cinder of the sun that was. Big stars follow a little bit of a different track. So big stars, they live short and they party hard. Okay, so big stars will live maybe for only 10 to 100 million years. So the big ones, 10 million years. Compare that to 10 billion years for our sun. Okay, so 1,000 times shorter than the lifetime of our sun. Big stars will, when they end their life, they become a red supergiant, and then there will be a catastrophic explosion. Okay, and I'll talk about supernova in a minute. The star will explode as a supernova, and what's left after a big star is either a neutron star or a black hole, depending on how big the original star was. So for a supernova, the star must be something like 8 times bigger, heavier than our sun if you want to become a supernova. So we're talking about really big stars here. But how does this get us to our elements, the elements that are missing on the periodic table? So as I said, it all stops at iron. So this picture now is how much energy it takes to bind 2 atoms together. It's sort of like the work you have to put in to sticking 2 atoms together. And we can see all the red dots here. They're being built up from the stuff from the Big Bang, hydrogen, helium, carbon, oxygen, silicon, all the way up to iron on this curve. And then after iron, the blue dots, the binding energy starts to fall off. So iron sits at the top of the mountain, really. So on the left, we have nuclear fusion, sticking atoms together to make iron. On the right, we come the opposite direction, nuclear fission, splitting atoms apart to become iron. So iron's the key point. It's the most stable element in the universe. So fusion to iron generates energy, right? And then fission also generates energy. But to make elements heavier than iron, to go into this blue part of the picture, we need to add energy in ourselves. If you want to push 2 iron atoms together, we have to add energy into the reaction. Stars don't want to do that. They're power stations. They want to be efficient. So stars stop with the production of iron at its core. Okay, so at the end of a star's life, basically what we're seeing is this onion-like structure for the star. So we're thinking about a big star here, okay? It's like a 20 times heavier than the sun, so a really big star. So it's always this competition between gravity trying to squash the star down and the star pushing back by making nuclear reactions and sending radiation out to fight against gravity. So gravity squashes and the star pushes back by burning hotter and hotter. The problem is when you get to iron, you can't create any new elements. It's the end of the road. You end up with this onion structure going from the lightest elements, hydrogen, helium, carbon, neon, oxygen, silicon, and a core of iron. And as the star gets older and it burns more of its stuff, it gets more and more desperate trying to fight against gravity. So a big star will maybe take 10 million years to burn all its hydrogen in the core into helium, and then about 500,000 years to transform its helium into carbon, 500 years carbon to neon, a year to transform the neon into oxygen, a mere 6 months from oxygen to silicon, and then in the last desperate death throes of these giant stars, a day to burn the silicon into iron. And then you're stuck because the iron in the core won't react with anything else. Suddenly, the star has lost its fight against gravity, and the star will collapse under gravity, and it happens fast. It happens in about 2 seconds. when the star collapses here. It's a really catastrophic event. The core collapses, it bounces, it rebounds, sends shockwaves all the way through the atmosphere of the star, and the star explodes as a supernova. So a supernova is an exploding star, and a supernova, when it explodes, is one of the brightest events that we see in the universe. So this happened in 1987, on February the 23rd, in a galaxy very close to us, the Large Magellanic Cloud, one of our little satellite galaxies. And a star called Sangelik exploded. It was a blue supergiant, about 20 times the heavy in the sun. So on this picture here is an image of the sky taken a few days before the supernova. And if I was face to face with everyone here, I'd be asking for people to point to the screen and tell me, where's that star that's going to blow up? Can't see it, right? But a few days later, this happened. So that's the supernova. And immediately, it outshone everything in this galaxy. This was easily visible, and it was one of the brightest things in the sky. It doesn't last that long. It immediately starts to dim, this explosion of stuff. What it leaves behind is a supernova remnant. This is a blow up image here. You can see these two expanding rings from the shockwave, and you can see where the star used to be. We now have this supernova remnant. We know where this star used to be now is not a white dwarf, it's a neutron star. So it's a tiny, dense object, as heavy as the sun, but packed into an area of about 20 kilometers. So it's an extremely dense object, the smoking gun, really, of a giant star. So there's plenty of supernovas happening all over the sky. This one here, again, this is a lovely picture. This is the Crab Nebula. It was named in 1842. Because it looks like a crab, apparently. It actually corresponds to a supernova that was observed by Chinese astronomers way back in 1054 AD. But just like the supernova of 1987, this is a big star that's exploded. Now, when this star explodes, you've got extreme temperatures, you've got extreme pressures, you've got lots of free neutrons whizzing around, and suddenly it's a free for all for making the elements on the periodic table. In fact, every single element on the periodic table can be made here in these supernova explosions. So suddenly we've gone from this sort of half filled up periodic table to a periodic table where we're starting to look really like what we're used to in chemistry these days. So exploding stars in one form or another, and they come in different flavors. There's the big stars that collapse. There's smaller stars that have energy dumped onto them and then explode, but exploding stars in one form or another will create almost all the everyday objects on the periodic table. So all these green ones here as well. And we've more or less filled up the whole thing here, because what's left really is elements that are either created by radioactive decay of heavier elements, things like the ones in grey like polonium, radon down here, or the dark grey ones that are actually not made in stars at all. They're actually elements that we've actually created in our laboratories by artificially bombarding heavy atoms with other nuclei. In fact, number 118 down here, so organesson, was created only back in 1999 as a result of bombarding lead, which is Pb down here at 82, with atoms of krypton, which is up here at 36. So bombarding lead with atoms of krypton, they were able to create this new artificial element that's number 118 on the periodic table. Okay, but except for those artificial ones and a couple made for radioactive decay, everything else, basically, except for the helium, hydrogen, and lithium, is created inside stars of one type or another. So we think we're almost at the end of the story here, but we're not quite there. We're not quite there. So this is a little bit of an oversimplification one question to ask would be, what about the gold? Because everyone wants to know where the gold comes from. So there's a little caveat to this story. There are some other processes that can form the elements that are heavier than iron on the periodic table. Now, in particular, as this picture shows, we can have a collision of two neutron stars. So remember, the neutron stars are what's left over when these massive stars explode as supernova and end their lives. Now, if two of these neutron stars get together, they can orbit around each other, get closer and closer and closer, until in the end, they actually collide with each other. And this really will be the mother of all cosmic explosions. And sometimes we refer to these as hypernova. And it's possible that the colliding neutron stars can also create all the elements that are heavier than iron. They create this through what we call the R process, and that's lots of neutrons whizzing around, bombarding various nuclei, and basically allowing heavy nuclei to be formed before they can decay. So you need extreme conditions, you need high temperatures, high pressures to get this process going. But it's one of the possible origins of gold, and in fact the heavy elements in the universe would be colliding neutron stars. So just a little change to the table there, where we've added the yellow half shading to the periodic table. So here we have our periodic table starting from the Big Bang, the hydrogen, the helium, and the lithium, through beryllium boron created by cosmic rays. Then you have sun-like stars with the CNO cycle creating carbon, nitrogen, oxygen. And remember, carbon, nitrogen, and oxygen are the building blocks of humans. We're mostly made of these three elements. Then we have the massive stars creating the elements from fluorine, number 9, up to iron. As we've seen, the iron's the most stable element in the universe. So that's the stopping point from big stars. Everything else will be created in these giant supernova or possibly colliding neutron stars. So we can start to see why, some elements are more precious, we might call it, than others, or certainly rarer than others. Gold is almost 2 million times rarer than iron. In fact, all the gold must be produced in that 2 seconds of supernova collapse or emerging neutron stars. Both of these are relatively rare events. So we can see why gold is so rare in the universe compared to other elements. And in fact, if you add up every single atom in the universe from gallium, and that's number 31. So let's start from gallium, number 31, all the way down to uranium down here at 92. You still only get about 1/2000th of the total number of iron atoms in the universe. So everything really past iron is really extremely rare. And we also have to remember that iron and the lighter elements, when you compare them to hydrogen, helium, they're rare as well. So you've got this massive scale, where something is, millions of times more rarer than another element. So we can start to see why, on the Earth, why some things are rarer than other metals. It's simply because it's so difficult for stars to create them. So we can now really map out the life of an atom from its birth to the present day. So say, for example, we wanted to think about where the gold came from. So we wanted to make a gold, we want to make a gold ring. Okay, so let's say we have a very nice gold ring. Can we trace back the atoms that make that ring up back through time? Okay, so as a little aside, just in case you're wondering, this particular gold ring, it was not made in the fires of Mount Doom in Mordor. Okay, it started life in the Big Bang. Right, so our atom's life began in the Big Bang 13.7 billion years ago. And at that time, we're all hydrogen, or 25% are helium. We're mostly hydrogen. We're going to be a hydrogen atom. We were created in the first 3 minutes after the creation of the universe itself. And our atoms basically stayed that way for at least the first 500,000 years or so, where we had this picture of the baby universe, and we start to see the matter clumping together, starting to form the galaxies. So now our hydrogen atoms start to clump together in galaxies, and inside those galaxies, they start to clump together in gas clouds like this. This are the famous pillars of creation in the Eagle Nebula, about 7,000 light years from Earth. And this is a very famous Hubble picture. So this is where our hydrogen atoms at the moment reside, okay, inside these clouds. Now, these are star-forming clouds. They're going to collapse under gravity and they're going to form stars. And you can see even on this image, you can see inside, you can see like on the edges, if you've got really good eyesight, you can see sort of like these circular regions this is where new stars are blowing away the material around it to form new stars. Okay, so we're a hydrogen atom in the universe. Maybe we're 300 million years after the Big Bang in the cosmic dawn, and we're going to collapse to form stars. Say we collapse to form a star like our sun. So we live in that star, you know, for a very long time. When that star finishes its life, it doesn't explode as a supernova. It becomes a red giant, and it expands as one of these planetary nebulae. Now, in this particular case, our hydrogen atoms didn't sit in the core of that star, so we were not converted into helium. We stuck as hydrogen atoms, and our hydrogen atom was thrown back out again when this star expanded back into space again. So we're floating in space again. Maybe we meet some other hydrogen atoms, and the whole process repeats itself. We get stuck in one of these massive star formation clouds again. This particular star formation region now is the Orion Nebula. It's about 1,300 light years away and about 24 light years across. It's a site of massive star formation. It's one of the most prolific areas of star formation that we know of in the entire universe. So our hydrogen atom again was mixed into this giant gas cloud that again collapsed under gravity to form another star. And this process might be repeated again and again and again, but eventually one of our hydrogen atom might end up in the core of a star. And let's say it's the core of a massive blue star. Blue star, for example, like some of you have heard of the star Rigel. It's a blue supergiant star in the constellation of Orion. It's actually the brightest star in Orion. It's about 18 times as more massive than the sun. So our hydrogen atom now lives in the core of this star and is slowly being processed through carbon, oxygen, silicon, and finally processed into an iron atom. Okay, so now we know already that when we get to iron, it's the end of the show. This star is going to explode in a supernova in the mere blink of an eye. These stars, these big blue giant stars, only last about 10 million years or so. It's a mere blink in the cosmic eye. So the star ends up as a supernova, leaving behind a neutron star. So maybe either in the supernova explosion or perhaps from a collision of the remaining neutron star with another neutron star, our atom is bombarded with high energy neutrons and eventually is transformed into gold. So we've reached our goal from hydrogen to gold through 3 or 4 easy steps through stellar evolution. But still not the end of the story. Our gold atom floats through space. And again, the process repeats itself again. We end up in a gas cloud that's going to form a star. But this time it's a little bit different. We were a bit late to the party and we didn't quite make it into the star itself. Our gold atom got left at the edge of the cloud. So the star's formed and we're basically in the leftovers of the cloud here. This is a protostellar cloud. And eventually this cloud will also collapse under gravity. And the disk of material around the young star starts to clump together into rocky objects. And then these collide again and again, slowly to build planets. And we could imagine our gold atom here happens to clump together to form a rocky planet, maybe the 3rd rocky planet away from an intermediate sized yellow star, just like our Earth. So our gold atom eventually ends up in the Earth's crust. Perhaps it will eventually end up as trace gold in your own body, or maybe it'll be dug up and it will be made into the gold ring that we were getting all excited about. So we've traced that atom now from the Big Bang all the way to the gold ring that we created over a journey of about 13.7 billion years. So it's been going for a long time to finish its journey. And this really, brings us, to a conclusion of the periodic table here. So we've seen indeed that all the elements we see around us, the things we're made up of, the carbon, the nitrogen, the oxygen we're made up of, all the trace elements, all the rare precious metals in the Earth's crust, like the gold and the platinum, all the rare earths that we use, for example, things in our mobile phones that we rely on so much. All of these were made in stars, or if they weren't made in stars, they were made up in the aftermath of exploding stars, or perhaps colliding neutron stars. So in conclusion, we can say, with confidence, yes, we are all made of stardust. But if we were being a little bit pragmatic about this, and we know now that the elements were forged in the nuclear furnaces of stars, where the fuel is the hydrogen and the helium, and really that makes us, in fact, we're all made of nuclear waste, which isn't half as it's not half as romantic as saying we're made of stardust. And I did think, would it be viable to sort of like, if this was on t-shirts and stuff, but somehow I don't think I don't think a t-shirt with "we are all made of nuclear waste" would quite have the impact of these like nice fluffy "we're made of stardust" t-shirts. And I think that brings us to the end of our journey, and thank you very much.
What a wonderful ending. Thank you so much, Chris. That was really, really interesting. We have a number of questions that have come in, so I think we'll crack on with them as soon as we've got 10 more minutes left. The first one, Brian has been waiting very patiently since 6:38. Are there sufficient neutron stars that cannot be detected because they are dark and cool for them to be part of dark matter?
Okay, right. So that's a
Chris, can I just ask you to stop sharing your screen, and we can get you bigger on the screen. We can see more of your face. Brilliant, thank you.
So that's a good question. Indeed, the answer's certainly yes. I mean, neutron stars don't shine particularly brightly. I mean, they're very visible if they're spinning as pulsars. They're like cosmic lighthouses. But certainly there could be lots and lots of neutron stars around in the universe that are too dark for us to detect, and they could make up some of the dark matter. But when we talk about the actual dark matter in the universe, being something like 6 times more abundant than the normal matter, a neutron star is still on the periodic table. Okay, so it's not dark matter, it's not exotic dark matter. So even though it might be dark and it might make up some of the dark matter, it doesn't help us at all in solving the mystery of like weighing up the universe, because the dark matter that we require to weigh the universe properly is certainly particles that are not on the periodic table. It's going to be something completely exotic that we've never encountered before.
That's a whole other talk then, basically. I hope that's answered your question, Brian. Gillian asked a question earlier on, but I think you've already answered it about how do the elements like gold end up on Earth, but she did recognise then that you went on to tell us about that. Yeah. We've got one here. Does gold being so unreactive add to why it is so rare?
Not, I mean, it is an unreactive metal. It doesn't really attribute to why it's to why it's so rare. I mean, the reason it's so rare, and it's not special. Gold isn't special compared to all the other elements next to it on the periodic table as well. I mean, they're all rare. They're all rare, and this is also the reason why things like silver, platinum, etc. are also precious metals. So being unreactive is chemistry, whereas what we're talking really about, the formation, is really physics. Yeah, so it doesn't really contribute.
Great answer, thank you. Another one here, how do elements from the stars get into our body? So
all the elements from stars, when the stars explode, they're all thrown out into space. Some of these elements fall into gas clouds that will eventually form planets around new stars. And once these planets are formed, it locks in certain elements. In fact, it locks in the heavier elements. We actually we lose a lot of the hydrogen and helium, and we're left with a lot of the heavier elements that go into the formation of the Earth. And for example, the elements that make up our body, they're not ours, right? I mean, they've been recycled millions of times through the Earth. I mean, there might be a gold atom in my body that perhaps used to belong to some bacteria that 3.5 billion years ago. And when that bacteria died, that atom was recycled and went into other animals or plants, etc., and ended up in humans. So we borrow the atoms for our lifetimes. Then we have to pay it back to the Earth afterwards.
Gosh, that's just crazy and a bit mind-blowing. You mentioned earlier on about the big shiny stars, the really sort of huge ones. They live short and party hard. I love some of these quotes that you had. Am I right in saying there's a star out there in the TRAPPIST sort of lineup of planets and the star, that it's not a really bright star, it's a slow burner, and I've heard that kind of star that is less bright and it's just sort of quite mediocre is going to be one of the longest lasting stars that we'll ever see in the universe. Is that right? Yeah.
So the star's lifetime is basically, it depends on its size, its weight. So the big blue ones, 10 million years, stars like our sun, 10 billion years, and stars like in the TRAPPIST system, the star in the TRAPPIST system, which is a planetary system with 7 or so Earth-like planets going around it, is what we call a red dwarf. And the red dwarfs are tiny. They're the bottom end of the size scale, and they will basically last forever. So in terms of the elements, the red dwarfs don't enrich the universe at all, because they're a bit selfish. They hang on to all their stuff for their entire lives, and they just stay there.
Reliable, that's what we like to say. And another thing that some people normally ask is that when we see pictures of the universe, and you've shown some really beautiful graphics on this presentation tonight, are those colours actually that colour? And how, if so, how do you know what colours things are? Like the pillars of creation is kind of dark greens and browns. So
it depends. It depends on the telescope that you're looking with. So a lot of the Hubble images can be real light. A lot of the optical telescopes we use on the Earth are real light. I mean, often these images are enhanced as you move to different colors. So for example, if you've got infrared lights, what James Webb will mainly be looking at, we can't see infrared light. So anything you see from James Webb will be a false color image. And we give it a best guess, because if we burn hydrogen in the in the laboratory, we know what color it burns. If we see it in space, we can tell what color hydrogen is as well. So blue on the Earth and blue in space is the same, because chemicals burn the same way.
Gosh, that's such an interesting answer. Phil's actually asking, when the Earth gets swallowed up, does that mean that we will eventually all become parts of stars once more? And I'm imagining this is the case because it's this recycling thing that happens.
Yeah.
Yeah.
So yeah, space is very good at recycling. So eventually, and again, this is over billions of years. But if the Earth gets swallowed up, if it gets disintegrated, all our atoms will pass back into the solar cloud. These atoms will pass through space, congregate with other atoms, and then gravity will pull us all together, and the whole process will start over and over again. So you never know what you might end up with, or what you might end up as in the future.
Kind of horrifying and exciting all at the same time. We've got time for one more question here that's just coming from Catherine. How many generations of stars did it take to form the material that went into our sun?
So that's a good question again, and we're not completely sure of the answer, because we don't know where our star was formed. Because I mean, stars like our sun, we've only gone through one generation in itself, because it's 10 billion years in its lifetime. So we know that we must be built up from the short-lived stars. So if we think of a star that lives 10 million years, and the age of the universe is 13 billion years, you could have gone through hundreds of generations of stars to make the Earth. We have to factor in, obviously, that once these big stars explode, these things float through space for millions and millions and millions of years. But certainly many generations could have gone into the stars like our sun. Yeah. I mean, we know that the heavy elements, we know the stuff like gold must be formed inside very violent events, and there's no violent events near us now. So we're looking at many eons ago and many generations.
Yeah, and yet we can create violent events on Earth by making more elements that you can't be made in the universe.
Indeed, yeah.
Inside machines.
Yeah.
Like
Inside machines,
accelerate.
yeah. I mean, these things, I guess, they could be made in the universe as well, but we never see them because they don't last long enough. So they're very fleeting. They're very fleeting. We don't see them in space.
Amazing. Well, on that note, I think we need to wrap up, but that's been so interesting. I think we could stay here all night asking questions. I personally feel like I've learned quite a lot tonight. If I'd had a chemistry teacher like you when I was at school, I think I'd have taken the subject a lot further because it's actually really, really interesting. So thank you for bringing it to life. Thank you for an amazing presentation and really great graphics. And yeah, just thank you so much. For everybody else who's still with us and watching, thank you for staying for the whole hour. It's been really fascinating. We are not going to have a Talk in Science online in February because we're going to take it out on the road into the communities at half term. This is something that we try and do a couple of times a year for people who can't get to the lab or who can't get online. So trying to reach different audiences. So if you please bear with us with that. I'll certainly let you know the details of all this that's going on through our mailing system. But we have a fantastic talk lined up in March. So there's much more to come and many more exciting talks. But for now, thank you so much for attending. And we hope to see you next time. Bye-bye.